is a great seminar series. So golden speaker, I'm not sure I'm a golden speaker, but I will try to give a talk on soft materials translation for health and sustainability. Xuanhe Zhao from MIT. The mission of my lab, merging humans and machines. The opportunity we see over the last century, there are great advances in terms of understanding and engineering human body, biology, medicine, genetics. This list goes long. Similarly, in the domain of machines, semiconductors, electronics, internet, robotics, AI, this list goes long. However, there's a huge gap in between. And this is the opportunity and the challenge that we see, and we try to merge humans and machines. Potential impact, better health, that's something we all want. Now, if you think about all the way from wearable devices to medical equipment to medical implants, these are machines trying to merge with the human body over the time scale of a few hours to days to months and years, right? Over the last century, we developed more and more sophisticated machines. The interface remained the same. Metals, ceramics, glasses, plastics. We have not changed the interface too much. What if we can design much better interface to truly merge these machines with the human body? Can we, for example, monitor COVID effects on multiple organs at home, right, fighting this pandemic? Continuously image heart diseases with wearable devices, remotely treat stroke within the golden hour. Right? These are the leading causes of global death. Right? Can we achieve this kind of impact? Understanding the brain is another potential impact. We have 86 billion neurons inside the brain. Right? The state-of-art brain-computer interface can only interface with around 3,000 neurons. Right? Neuralink is one such an example. Right? If we can design much better brain-computer interface, can we interface with 1 million neurons in a living brain to better understand the brain and the intelligence? Right? Now, if we think even further, right, all the way from AI, robotics, VR, an essential component is human-machine interface, right? And that will impact the future of humans and the society. So, many other potential impacts, but we see there's a great opportunity on this interface, right? Then what is the challenge, right? So it's quite a straightforward challenge, right? Due to materials and biology, right? Human body are mostly based on soft, white, living materials. On the other hand, traditional machines are mostly based on hard, dry, abiotic materials, right? Fundamentally contradictory material properties. How to merge them together closely. Right? So that's the challenge. Now, let's take a closer look at a major component of the human body. For example, here, we plot different components of human body as a function of their rigidity. You can see, except teeth, bone, and nails, all other components of human body are soft materials, with modulus on the order of a kilopascal to 10 megapascal, containing 70 to 90% water, and these are living soft white materials. They can grow, sense, respond, self-heal, and these soft materials are also very robust. Under millions of cycles of life in our overall lifetime, they maintain high robustness, well-being. So these are the fundamental materials of the human body. Based on this understanding, we propose a very, I would say, this is a very bold idea. We want to merge human and machines with jellos, with, or broadly, soft materials with very similar mechanical and physiological properties as different components of the human body, so that these kind of soft materials can form long-term, high-efficacy, even non-fibrotic interfaces with diverse human tissues and organs. At the same time, you make this jello very robust so that you can integrate sensors, actuators, computer chips, even robots within this soft material interface, and use that to form long-term high-efficacy interface between humans and the machines, right? So, sounds crazy. How do you make a jello, right, to be part of human body, part of machines, right? We've been doing lots of fundamental research. It turns out that this is also a great topic in terms of mechanics and materials, right? Previous material people has been focusing on steel, ceramics, but then the fundamental question is how to make soft material containing 70 to 90% water to be tough, to be strong, to be fatigue resistant under millions of cycles of load, to be adhesive to both human body and external machines, to be active so it can interact with different components of the human body, to be electrically, optically, acoustically transparent between the human body and the external machines, so it can facilitate this communication. Right? We publish many papers to really lay out the foundational design principles of these properties based on fundamental principles in physics, in chemistry, and in bioinspiration. Then in today's talk, I will use a few examples about the translation, because this is a golden speaker series of TIO. But when I discuss this potential translation, I will discuss the fundamental material design as well. Yeah. So the first translation is this realistic tissue phantom for training radiologists. Right? This is the lead inventor, Dr. Hung Yik, currently CTO of Xuanhe Zhao. Right? So the story is this. At 2016, at that time, right, my lab working on soft materials, right, we invented different types of hydrogels, but the hydrogel dry out too quickly, right? If you put it like a piece of jello, on a plate, they will dry out quickly, right? So then we invented this idea of a hydrogel elastomer hybrid. Right? The elastomer is like the skin, which is hydrophobic. It can lock the water inside the hydrogel. So once you form this hybrid, we also form very strong bondings between the hydrogel and the elastomer. So we published this paper in 2016. We patented it at TIO. Thank you, Ben. After the publication of this paper, CRS, this tissue phantom company, contacted us right away because they are trying to develop a next generation tissue phantom to train doctors. Right? You cannot train radiologists with patients. You need to train them with a realistic phantom. They can use a soft rubber to make phantom, but it does not contain the water. They want to use a hydrogel to make the phantom, but the phantom dry out too quickly. Then they try to put this elastomer skin, they detach, they debond. Then you do not have a reliable phantom. They license our IP even before the patent has been granted. They licensed it, and then they make in the 2017 into FDA-approved products of a tissue phantom. And because CRS is the leading phantom supplier of US, even the world, this is currently the leading tissue phantom for training radiology all across US. And especially during this pandemic, right? We know this CT ultrasound is extremely important for diagnosis the COVID progression. For example, in the lung. It turns out that many of these radiologists were trained by our tissue phantom. So that's, you can see, it's really I like this story quite a lot. By serendipity, we published this paper. Then over years, we see this translation into FDA-approved product, and then impact even during this fighting this pandemic. So that's one example. Then example number 2, bioadhesive to replace sutures. Right? So this is the motivation is this. There are over 310 million major surgeries per year. Most of them require suturing to close the wound. However, we know suturing can cause tissue damage, pain, scar, infection, and leakage. Right? Suturing is also unsuitable for rapid hemostasis, robotic surgery, or bioelectronics. Right? So this is our invention. So literally, we invent a double-sided tape or Scotch tape, but work with wide dynamic human tissues. You can see we can adhere this on this kind of wound across the body, skin and the internal organs. Then this will quickly seal the wound. It can even contract the wound together to facilitate the healing process. Not only that, so this is an animal model. This is a beating heart of a rat model. You can see during this experiment, they poke a hole on the heart with our material. It can quickly seal this wound and stop the bleeding. So without forming, the clot, you just, directly seal it. So this is really rapid hemostasis. So this is the technology platform, and then we filed around 6 patents at TLO, and my student and I co-founded Xuanhe Zhao. We licensed this IP, and now Xuanhe Zhao has multiple biomedical and cosmetic products in the FDA approval process. Because this is really a technology platform, we have diabetic wound healing products. We have hemostasis products in collaboration with Amor Pacific, the second large cosmetic company. We even have cosmetic products in the pipeline. And not only that, Xuanhe Zhao's inventions and the technologies also recognized by various awards. There's a college-grade inventor competition, MIT Sloan Health Innovation Prize, Nature spin-off prize. People publish hundreds of papers in Nature each year. They only select one spin-off prize for the startup based on those papers. Xuanhe Zhao won the one 2022 to 2023. So that's the second translation story. Then I will tell 2 stories in the pipeline, in the process. So the third one is soft medical robots. So here is the motivation. Stroke is globally #1 cause of long-term disability, #2 cause of death, 15 million cases per year. Basically, 1 in 4 adults, in the audience in our lifetime, we will have the chance to develop a stroke, So that's the potential impact. Stroke is reversible if you can treat stroke within this golden hour, a couple of hours after the occurrence of a stroke, then it's fully reversible. However, if you miss this golden hour, then time lost equal to brain loss, Then the standard care, So this is the current standard care. It's called a thrombectomy, The neurosurgeon will make an incision on the femoral artery on the leg of the patient, and then insert this long guide wire all the way from the leg to the brain of this patient, to reach the lesion of a stroke, and then to treat the stroke, So this is an effective method, but lots of intrinsic challenges. #1, long training time for neurosurgeons, 4 to 7 years, Because you may ask, how do I navigate, all the way from the leg to the brain? There are lots of branches of your blood vessel. The tip of this guide wire is a J shape, Then the neurosurgeon rotate the guide wire from outside the body. Then this J-shaped tip rotate inside the body to the desired branches to navigate to the desired branches. So it takes a very long training time to master this, practice. Then these neurosurgeons, they only work in this called tertiary centers, Major medical centers. They are unavailable, especially in rural areas, For example, in Boston, we are fortunate. There are Harvard Medical School. We have this kind of centers. However, in Maine, New Hampshire, we need to transport the patient all the way from those areas to Boston for treatment. And during this transportation, the majority of the cases miss this golden hour. So that's an intrinsic challenge. It cannot be solved. Then for these heroic surgeons, they also suffer. They suffer from accumulated radiation, Because they need to work under this X-ray fluoroscopy to see the exact location of the guide wire and the blood vessel to navigate it, For the patient, it's one time. For these neurosurgeons, it's their whole career. They suffer from this accumulated radiation from X-ray. These are intrinsic challenges. So my student, Kim, so he noticed this challenge, and we propose a dramatic different idea to treat stroke. So we call it a tightly operated, in future even autonomous robot. Right? So we design a guide wire robot. Right? So you can see, but the shape of this guide wire robot now is straight, not a J-shaped tip anymore. Then you may ask, then how do you navigate it? We embed this so-called hard magnetic particles, right? So imagine these are small magnets around the tip part of this soft guide wire robot. Then when you apply external magnetic field, so this is like a soft, magnet. It can bend along the applied magnetic field. Then this on-demand bending will navigate this guide wire to the desired branches of the blood vessels, right, in the brain. So that's the idea of this robot. Then it requires lots of fundamental studies, right? How much this robot, this guide wire will bend under magnetic field. We need a model. So these are fundamental mechanics, physics. We developed a quantitative model. You can see these are simulation results based on the model. These are experimental results, data. So this is very important, right? Many students want to become, especially PhD students, want to become an entrepreneur. But don't forget the fundamentals, right? Because as an MIT PhD, that's your strength. So with this, we have lots of confidence about our system. Then this model later can guide the design and the control of this robot, right? So that's number one. Then number two, now we need to design this robot, right? Because this is a guide wire. You want to apply as little magnetic field as possible to achieve the bending you want. Then the question is how to design the most agile hard magnetic soft robot for endovascular surgery. This is a clinical problem, right? How to define most agile. So we collaborate with Dr. Aman Patel, who is the director of cerebrovascular and endovascular neurosurgery at MGH. To him, the most agile robot will reach the largest workspace. This is also actually intuitive. You want this robot under low magnetic field reach the largest possible area so that you have the highest flexibility for navigation, right? Then we convert this clinical problem into a scientific problem, right? Design problem, right? Then the problem is how to design the patterns of these small magnets inside this robot so that you can reach the largest workspace, right? So then that become a problem in my domain. So we use, based on this model, we can do thousands, even millions of simulation, right, for different random configurations. Then you can harness, right, the most advanced AI algorithm or genetic algorithm. Use that to optimize this design. Eventually, you can see this is the optimized pattern of the magnetic particles. Around the very tip, you have a high concentration of magnetic particle. In the center part, you have very low concentration because this gives the flexibility. Then around the end, you have another high concentration. So two flexibility, together, so you can reach the largest area. But with this model, we can accurately calculate what's the optimized, design to give you most agile hard magnetic soft robot. Right? So that's that. Then the third part, fabrication, manufacturing. Right? If you want to translate, you need a product level quality robot. Right? We use 3D printing. Now we have even more advanced, this fabrication process. The key idea is, so you use this direct ink writing. Then when you print this polymer ink out, you also couple electromagnet around the nozzle of the 3D printer. Then this electromagnet can reorient these magnets inside the ink you printed, so that you can program the magnetic patterns you print out. Right? So this also published in Nature, also even become the cover of Nature. Right? So we not only translate technology, we really have foundational papers, foundational, I would say fundamental science behind the technology that we translate. So then with that, it's about, implementation of the whole system, right? So we developed this full system, so fluoroscopy. We use a single robotic arm to hold a magnet, this is a magnet, to apply the external magnetic field, right? And this is a joystick controller that will control the position of this external magnet. Then we have another unit to advance or retract this guide wire robot, right? So you can see the navigation, this bending, and the advancement, retraction are decoupled. So they are not together, so that you can control them individually. So with that, let's see some preclinical results. The first one is tightly robotic aneurysm coiling, right? So this is the aneurysm in a phantom, in this phantom model, right? If you do not coil this aneurysm to protect it, it may burst. That will give the patient a hemorrhagic stroke, right? Then how to navigate these coils to this aneurysm? You can see this is under C-arm fluoroscopy. We first navigate the robot all the way to this aneurysm. Then in the second step, we will deliver the microcatheter, which is a small conduit, right? So around this guide wire robot, so then you deliver this small conduit to this the aneurysm that you want to treat. Then in the third step, you withdraw the guide wire robot. Now you deliver this platinum coil to coil up this aneurysm, right? You can see the whole process was operated by this robotic system, and the operator, the neurosurgeon, is in another room. In the future, we even hope this is in another city, so we can remotely treat a stroke patient, right? And also, this is VR, this is a virtual environment, right? We can visualize the whole setup in this virtual environment, and also it can, make sure there is no collision between the robotic arm with the patient or with the other setting, right? You can see very quickly you coil this up. Another case is, clot. This is ischemic treatment, right? So with a similar process, you deliver the guide wire robot, and with this is a stent retriever, right? It's like a fishnet, capture this clot, and then you retrieve the clot together with the robot back to the body. Then you clear this stroke, right? So not only that, because we are targeted at a translation, we want to make this technology as mature as possible. We tested this in pig models, porcine models. So this is the pig forearm. So in this this flexed position, this is a mature protocol to simulate the blood vessels, arteries inside the human body. Now use this model. So we do the navigation. You can see this pig is covered by this white sheet. You cannot see it visually. You only can see the blood vessels, the guide wire robot through X-ray fluoroscopy. And here is the robotic arm with the magnets. You can see. Then by positioning this magnet to desired locations, you can remotely guide the navigation of this guide wire robot to desired branches. This is a quite a challenging navigation, even for manual operation. But with this robotic system, we can quickly navigate this guide wire to desired location. And probably you cannot hear this beeping sound. I'm hearing this beeping sound, which is the heart beeping of this pig model. So it's still alive during the whole operation process. Then let's compare with standard care, compare with manual operation. Number one, impressive comparison is this. As I told you, for those manual operations, it takes over 4 years of training of those neurosurgeons, right? 4 to 7 years, right? For this robotic system, because many of those neurosurgeons, they are very familiar with this video game. So only take them around an hour to train with this robotic system. And then they are, become experienced. They can operate this robotic system. It's very intuitive, right? Then I want to quote our collaborator, Dr. Aman Patel. With his help, they means his trainees didn't need my thousands of hours of surgical expertise to approach my level of skill. So imagine the potential impact if you can use this kind of robotic system, train many neurosurgeons in shorter time, and then deploy this robotic system all across the country, really save stroke patients within the golden hour. Not only that, if you look at the performance, right, in terms of performance, one most important factor is the number of undesired steering maneuver. Right? So, for example, this guide wire touching the aneurysm, touching blood vessel, that's undesirable. Right? You may even pierce a hole on the blood vessel. So you want to avoid those. Right? For manual operation, many of those undesired steering are unavoidable, intrinsically unavoidable, because you need to rotate this guide wire robot inside a narrow blood vessel. Right? However, for the robotic system, very quickly you can decrease this to zero due to intrinsic different operation mode. Right? So complication rate for this kind of neural operation, right, can reach up to 10 to 20%, mainly due to undesired steering. Right? Imagine the potential impact if we can deploy widespread this kind of robotic system for stroke treatment. Then what is the next step? Right? What can be the future? Right? We believe we can harness modern technology such as AI to further relieve the cognitive burden of the neurosurgeon, to further automate this robotic system. So here is one example. Right? If you think about this problem, right, it's quite straightforward. Under high resolution medical imaging, right, you know the current location of your guide wire, you know the desired branch of the blood vessel. Then the problem is really what magnetic field I should apply to bend my guide wire to this desired branch. Right? That's an inverse problem. Again, it's a difficult mechanics problem, but with the current neural network, we can do millions of simulation based on the model, and then use this model to train this neural network, so that the neural network can predict the control variable, apply the magnetic field, so that to bend this guide wire to the desired location. Right? And then you may say there can be mistakes. Then the neurosurgeon can play the role of intervention, stop the machine navigation, and then use a joystick manual operation of this robotic system. Right? So that's our vision. Then here is some preliminary results. You can see in this whole process, no human intervention anymore. So this is fully automated. You can see this is like a self-driving of Tesla. So you are navigating inside the blood vessel. This is a location that requires some navigation. Then the system will call the neural network calculation. Then navigate to the next location that requires navigation. Then you have another predicted applied magnetic field. You navigate around this. Then you go to here. So I would say this is possible, and this technology will develop in parallel as the translation of the mature joystick control technology, so that they will go hand in hand. I believe that's the process of making impact with this kind of technology. So this is our philosophy. Soft robotics plus modern technology such as AI can give us a future precision medicine, especially in the sector of endovascular treatment and this endovascular navigation and treatment. Right? So scientists, we are on board because we are doing science for curiosity and also for societal impact. Surgeons, they are on board, right? Because they know they cannot be fully replaced by robots. It's impossible. Lots of work requires their attention. However, they can be empowered by software robotics and AI. They can save more lives safer, faster, remotely, with much less training time. Right? Patients, time lost equal to brain loss. Right? You can see very rarely all stakeholders are on board, and the other technologies such as imaging, robotics, control are all converging towards this extremely important societal challenge. So I believe we will move this forward with the effort from different sectors of the society. Eventually, the goal is to treat stroke patients within this golden hour. Then this is also a fundamental challenge in science and technology. Right? So I want to use this analogy just to inspire the audience. Right? So currently we can genetic edit cells on a molecular level. Right? CRISPR is one example. However, currently we do not have a robotic system can minimally invasively edit the full human body on a cellular level. For example, remove a tumor from any place of the body minimally invasively. Deliver drugs, cells, even CRISPR to any location of the body minimally invasively. Right? Now, if we look at this blood vessels, right, the piping system of the human body, right, this is really high pass highways to different locations of the human body. We can miniaturize this robot all the way down to the length scale of 10 micron. Then it's really possible to navigate to different locations of the human body, full robotic, minimal invasive editing of the whole human body on a cellular scale. So that's just a challenge I want to pose to the audience for very talented students to think about your future research projects. Then I will discuss the last example of translation, wearable imaging. Right? So I will begin this with the recent very hot topic, stretchable electronics. So the idea is nowadays people make electronic devices into this thin conformal form factor to the skin so that it can stretch together with the skin, and people use this kind of devices to measure EKG, EMG, EEG, heart rate, temperature, sweat, many physiological parameters of the body. However, these devices are not for imaging deep organs, and we know how important imaging modality is for diagnosis of diverse diseases. Right? Then, indeed, recently, people begin to try to make ultrasound into stretchable form factor. For example, Professor Xu's group at UCSD make a stretchable ultrasound so that this ultrasound probe can stretch together with the skin to image internal organs. However, it suffers from intrinsic challenges. Number one, acoustic wave is directional. Stretchable ultrasound probe need to conform to the skin, right, parallel to this skin. The resultant imaging direction is not optimized. Right? You can see here, you miss the major reflection of the incoming acoustic wave. Number one, intrinsic challenge. Number two, ultrasound imaging requires accurate transducer positions. You need to know exact location of each of those transducers. Right? However, the stretching, right, like stretching the image sensor of your cell phone, will introduce significant imaging errors. So these are intrinsic challenges that people know. So in 2022, we propose a fundamentally different idea. So we call it a bioadhesive ultrasound. Right? Instead of making the ultrasound probe to be stretchable, we make it into a thin, rigid form factor. Right? It's an ultrasound patch, but thin but rigid. Then you may ask, how do you conform that ultrasound patch to different locations of the body? Then we introduce this soft bioadhesive couplet interface between the machine and the human body. Right? So this couplet can provide a skin adhesion and conformation because it's very soft. It deforms together with the skin. It can give us optimized imaging direction. So think it this way. we can make this soft coupling to be different shape so that you can really optimize the imaging direction. No probe stretching or image distortion, and it can enable functional communication between the human body and the external machine. So that's the key idea. Thin, rigid ultrasound probe and a soft bioadhesive coupling. Right? So, then with that, I'll first tell you the big picture. We transform ultrasound imaging. Right? So this is one of the most popular imaging modality in medical applications. Right? But in the current practice, the clinician use a thick handheld ultrasound probe, spread liquid gel on the patient. The patient needs to go to a hospital to take a snapshot imaging. And the patient is also in static state, right? Cannot move around. Right? We transform this technology into something that is wearable, right? You can adhere this bioadhesive ultrasound patch to different locations of body. You can wear it even at home or in hospital. Now the imaging become long-term continuous, right? You can literally image organs over hours, even days. And then it's hand-free. Now you don't need to use a hand to hold this probe. Then you can put multiple patches on the body, and the patient can undergo dynamic body motion. So we transform ultrasound imaging into this new possibility, I would say. Then the essential technology, right? We need to design this bioadhesive coupling. So this is quite challenging to design, right? How to design this to be adhesive to both external machine and the human body at the same time with very low acoustic attenuation coefficient, right? You want the loss of this acoustic energy to be minimized during this communication between the human and the machine, right? You can see this is our design. These are black dots, right? In comparison with our existing commercial products, right? These are much higher across frequency from 1 megahertz to 10 megahertz, much lower attenuation coefficient of Bose coupling. Right? The reason is we designed this hydrogel elastomer hybrid that is adhesive to both human body and the external machine, and you can really minimize any air bubbles or defects on the interface to enable this very low acoustic attenuation coefficient. Then we further design this tunability of this Bose coupling. Right? You can see we can tune the location, position, and the angle of your imaging probe. Right? Then once you achieve optimized imaging direction, then you freeze this coupling at this state. It locked at this state and give you this optimized imaging over hours, even days. So that's the adjustable ultrasound or tunable imaging direction. Then after that, we designed this thin, rigid ultrasound probe. Here, for the design, we even use 3D printing because for 3D printing, it allows us to have rapid prototyping. In one day, we can try 10 generations of a design to achieve the optimized ultrasound probe. Right? With this ultrasound probe, right, the power is very low. Right? I compare the power of this ultrasound probe with Apple Watch. Because Apple Watch is multifunctional, the power is on the order of 100 milliwatts. The power of Bose ultrasound probe only on the order of 10 milliwatts. And if you wire it on the body, over 48 hours, it does not change the local temperature because it's a low power. Any heat generated dissipate into air very quickly. Then the control system, right? Just to make this, technology to be translatable, we developed this fully integrated wireless portable control unit. It has memories, it has processors, it has Bluetooth to communicate with your cell phone. So the size of this is like a cell phone. So you put it in the pocket, connect to different patches with cables. Then this control unit will also wirelessly communicate with your cell phone, transmit the image to your cell phone. So with that, Now let's see the results. So this is the students leading author of the paper, right? Doing this bicycling. Then you can see we adhere this ultrasound probe on this on the neck. So this is for the imaging of a carotid artery. Right? Then you can see this is the whole system, right? Wireless communicating with this tablet. Right? So this is the imaging results. Right? Clearly, and the student is doing this bicycling. You can clearly see the image over long term, continuously when you're doing sports. So then what can be a few potential impact, right? Real-time monitoring of the lung over 48 hours, right? So this is for the first time, people can image the lung continuously over 2 days, right? So then the potential impact, if anyone diagnosed COVID positive, now you can put a sticker on the chest of this patient and send the patient home. Then for the majority of the patient, the lung image will look like this: thin, smooth pearl line, right? Parallel A lines. This means even though you got a COVID, no symptom into the lung, right? However, if the pearl line become irregular, A line condensed, that indicates lung infection. And for these patients, the system will give them a warning. At this time, they should go to a hospital for further treatment. So that's the potential impact, right? So then now we don't need to send all the COVID patient to a hospital. We can use this kind of a monitor system. And this is much before the blood oxygen level of the patient getting too low, because that is the result. This is the cause. This lung infection is the cause, so that you have early diagnosis of a COVID infection of the lung. So long-term continuous monitoring of a blood pressure waveform. We know 1 billion adults, or 22% of global population, have hypertension. Hypertension is the most important preventable risk factor for premature death rate. It's highly desirable to continuously monitor your blood pressure waveform. However, we know how challenging it is to continuously wear this, pressure, this cuff. It's unnatural. You need to pump pressure to the arm. So it turns out the blood pressure is correlated with the diameter of this carotid artery. With that understanding, now we just put one imaging sticker on the neck, image the carotid artery. Then we can continuously measure the blood pressure waveform, over long term. As a byproduct, we can also measure the blood flow rate. You can see this is in static state. After training, much higher blood flow rate and the blood pressure rate. So this is my systolic blood pressure over 48 hours. This is, we are making this really mature. You can see I do some exercise, the blood pressure go higher and then reduce quickly. Giving this golden seminar speaker series, getting nervous, my blood pressure, ramping up again. So then what's the potential impact? Then at this time, my cell phone will send me a warning. I either should calm down or take some medication. Closed loop, modulation of your blood pressure. So that's the potential impact. Then long-term real-time imaging of a cardiac dynamics, right? We know cardiovascular disease are #1 cause of global death. Right? Apple Watch made a breakthrough in this field by providing this long-term continuous EKG measurement. However, it turns out EKG can only diagnose around 22% of heart attacks. The majority of heart diseases requires imaging modalities for diagnosis, right? Especially this ultrasound imaging. Right? Then now we have the capability to really continuous image the heart over many hours, especially if you feel chest pain or uncomfortable. At that time, we can turn on the ultrasound imaging, send a video or images to our clinician for real-time diagnosis. long-term real-time imaging of muscles. Students love this capability because it can tell you what's the ideal point to stop your exercise. Right? We don't know. Usually we tend to overdo our exercise. However, ultrasound can tell you the optimal point in terms of the vascularization, in terms of the activity of the muscles. Then by certain AI algorithm, it can potentially tell you at which point you should stop the training. And then even after that, you can further observe image the progress, all right, the effect of exercise on your muscles. Right? So it can tell you how much exercise is sufficient or too much, right? Impact on sports medicine rehabilitation. Then many other examples. So this is the most recent example. Now we can stick 5 patches across different locations of the body. Then we image 5 organs all together. Right? This is over the summer. The students walking around the Charles River. Right? You see this very interesting correlations between different organs. Right? So here is one example. Right? The student drinks some water. You can see the gastric, the stomach increase in size due to this drinking water. The bladder maintain similar size. Then over time, the gastric size reduce, bladder size increase. Then around the end of this, this study, the student went to restroom. So you can see the bladder size decrease suddenly. So now you can understand different organ correlation over daily activity. For example, walking around the Charles River. So that's the potential impact. Then let's compare this with the state of art. Right? We compare the imaging quality of our bioadhesive ultrasound system with Butterfly, another MIT spin-off startup companies. Right? So you can see very similar imaging quality. So this is different organs, right? Very similar imaging quality. However, the bioadhesive ultrasound is long-term, continuous, wearable on dynamic subjects. Right? Not only we can achieve this, point of care ultrasound, we really enable new functionalities other ultrasound system cannot provide. Long-term, continuous, wearable on dynamic subjects. So then wearable ultrasound can be as hot as AlphaGo and CRISPR. It does not mean societal impact. It just means media attention to your technology. Right? So this is the Omnitric score of this Bowles paper after we publish it. You can see really similar level as a CRISPR paper by Doudna and Charpentier, and even similar to the first AlphaGo paper by Dimai team. Right? So you can see the society really pay attention to this kind of technology, especially wearable technology can enable new functionalities. Then we even care more about the world's top clinicians' opinion on our technology. Right? For example, Professor Eric Topol, who is our COVID hero. Right? If you are on Twitter, you know his contribution to this fighting this COVID pandemic. It's a very impressive new frontier about how we can use ultrasound imaging continuous to assess multiple organ system. It's a new window into the human body that we have never had before. This is anatomy. This is very different. We have never had a sensor with continuous anatomical imaging. And many other clinicians voice similar opinions about this technology. Then what's the next step, right? What's the future, right? So we know this is a state-of-art wearable devices, right? Apple Watch, for example, right? It can give you linear data, EKG and the temperature or others. Our vision, especially this startup Sonology, we believe future wearables will provide continuous imaging of diverse organs, right? Then you may ask, with such a huge amount of time series imaging data, how do you analyze them? Then AI, I think, will play a big role in analyzing quantification of those images, right? So the idea is you will transmit the image from the ultrasound system to your cell phone, usually is the cell phone, then the cell phone will upload them to the cloud or communicate them with hospital for real-time AI-based either image processing or even diagnosis in the future. Then just a few potential impact. Long-term high-resolution imaging of health and disease of a diverse organ system, chronic conditions, at-home monitoring of COVID and even long-COVID patients, observation of a tumor development, brain development, fetal development, preterm birth, women's health. In addition to talking about diversity, let's develop technology for diversity. Then eventually, this is the dream. This is a very challenging goal, but this is the dream of my lab and Xuanology, making ultrasound a wearable commodity for global health. Ultrasound imaging is such a powerful tool for diagnosis, for monitoring. There is no reason you have to go to hospital, to go to a clinician's office to enjoy this privilege. So we believe we may be able to make it into a wearable commodity for global health. Then with that, let me propose another fundamental challenge. So in science and technology, currently, we can achieve super resolution imaging of single cells, STORM and many other technology can provide super resolution imaging of single cells. However, human body contains trillions of cells. Those cells self-organize into tissues, organs, organ system. That's another level of imaging. Can we achieve long-term continuous imaging of a full human body over the time scale of days to months, both in healthy and diseased state? Can we achieve that? Because that will give you the full picture about your human physiology. So that's another level of understanding. And that, in connection with super resolution imaging and the genetics, can really give you a full picture about your health. So we believe that has huge potential in the future. And again, in the spirit of inspiring students in the audience, this can be a future direction that you can think about. Wearable ultrasound imaging can be one of such a possible technology. The results I showed you, now we begin to image different organs simultaneously to observe their correlations. In the future, I believe we'll have better technology, better data analyzing capability, better understanding of a human physiology. I also want to show another side story. This is really about the publishing paper and then potential impact and maybe translation. So after we published this bioadhesive paper, the Xuanhe Ocean Institute contact us because they want to measure the ocean. We understand more about the moon than the deep ocean. They want to send lots of sensors to selected locations of the ocean, and the ideal vehicle to carry those sensors are marine animals, because those are the regions that you are interested in. The region marine animals that will go are the regions you are interested in. So previously you can see these are suture holes, suture those sensors on squid, and then most of the time they kill the squid before you can release it. Then with our bioadhesive technology, now very quickly, you can stick this sensor on the squid. You can see the squid is not scared during this process. Uninterrupted, then you just release this. Then you can measure the data over the time scale of days, even months. So we deploy many of those sensors around Boston area. Lobster is a skate. If you go to legal seafood, see a lobster with a sensor, don't be surprised. That may be our sensor. Yeah, so you can see. So all this. So then you may ask, what's the potential impact? Now we can understand, we can at least as the first step, obtain huge amount of data about the ocean. So here, I will not go to details, but now with this interface technology, it's not only about merging machines with human body, it's also about merging machines with animals, with the nature, eventually understand the nature better for the goodness of sustainability. With that, I will conclude. So I discussed soft materials translation, the impact, especially soft materials with modern technology such as AI, better health, understanding and editing full human body, sustainable food, water, plastics, environment, energy, the future of humans and society. I discussed a few examples, more on the pipeline. I just discussed with Ben about the VR, about other technologies that are in the pipeline of my lab. And the acknowledgement, right? So research collaborators that I discussed in the talk, Professor Pradeep Sharma, Sean Chester, Aaron Mooney, because many of our research relate to health. We have a dream team of clinical collaborators: Aman Patel, Pablo Horka, Eris Webbs, Rafael Bueno, Frank Lozolfo, Christoph Nabzi, Deha Griffiths, Albert Kwong. And thank you funding agencies, especially TLO. So I would say TLO is an amplifier. You develop a technology in your lab through TLO, through the ecosystem of MIT, you amplify the impact, especially societal impact of your work. Thank you very much.